everyone. Welcome to the talk. So, as you can see, this is an NAC talk. Date is 30th August. Title is Stardust and Stardust, and a game of hide and seek. Just to be clear, we start this as humans, right? 9 minutes that. Okay. In this talk, we are going to talk about certain class of stars that are invisible. Notice the aspect. We are going to see, we are going to learn why that is there by the end of the talk. Also, as a based on the review paper by astrophysicist Van Michael. Okay, so I said class of stars that are invisible, right? So to understand why they are invisible, we are going to take the assistance of a guy that I personally don't know, but that guy. Okay, focus on that guy. We are going to show you what the invisible class of stars are. But before that, don't get all excited. We are not going to talk about black holes. There is a separate talk for that. And I'm glad it got cancelled because you can see that these stars that I am going to show you are the coolest invisible stars. Right? So when I say invisible, what I mean by that is we can't see it. From attending all the sessions, you know that there is much more to than being just visible. Right? There are other parts of the electromagnetic spectrum that we can't actually see. Right? So to see what actually this guy is showing, we're going to switch to a different. We're going to switch to a different part of the electromagnetic spectrum, and that is infrared. So now you see what is post-AGB stars. That is what we are going to talk about. Also, don't notice the text under the image, which changed when we switched to infrared. Yeah. So naturally, the first question that comes up is, what are post-AGB stars? But before that, let me illustrate why we can only see them in infrared, right? So, if you were told to find difference between these two pictures, would you be able to tell what the difference is?
See.
What?
The number of stars.
Yeah, number of stars. But to start with, they are the image of the same object, right? And they are also taken with the same telescope.
They are not as bright as it
Yeah. They are taken with the same telescope, but the difference is the image on the right is taken in infrared, and the image on the left is taken in radial visibility. So the reason for which you see more stars in the infrared image is not because the stars are directly emitting in infrared. They are emitting in visible like every other star. It's just that in the visible image, the visible light is getting blocked by dust. So you have all these stars, but they are covered in dust. So you can't see them in the visible. But dust allows infrared light, and it also radiates infrared light. And that is why you see all the stars in the infrared image. So now we have kind of indirectly established that post-AGB stars, which we are going to talk about, are covered in dust. So now we are ready to, now we will begin to answer the question, what are post-AGB stars? Before we talk about post-AGB stars, first we need to talk about what AGB stars are. Right? Because once you have AGB stars, then whatever comes after that is a post-AGB star. And so naturally the second question that comes up is, what are AGB stars? So to talk about AGB stars, we first need to talk about what stars are. So everybody knows what a star is, right? Basically, put a star as a luminous object that emits its own light, and it uses lighter elements into heavier elements to produce energy. So that the radiation pressure can balance the gravitational pressure and the star can be stable. So, okay, so for now, just know that AGB star is just a star in its AGB phase. Now, what do I mean by AGB phase? So, since a star runs on fusion, the energy produced by fusion, it basically runs on fuel, which is lighter elements. But since the star is finite, it also has finite amount of fuel. So eventually, through burning, it will run out of fuel. Right? So when it runs out of fuel, it dies. So between the birth of a star and the death of a star lies its life. And through its life, a star goes through many different phases of evolution. Different processes dominate in different phases of evolution. So, and in those phases of one of the phases is the AGB phase. So, to talk more about the actual phases, I'll introduce to something called as go ahead. Okay. First of all, I would like to make a distinction. Right? Not every star goes through an AGB phase. And since I've already spoiled it, the factor that determines whether a star goes through an AGB phase or not is its mass. Right? So the factor that determines whether a star goes through an AGB phase is its mass. For a better illustration, this is an image that shows how the fate of the star will be depending on its mass. So on the right you see, so the distinction is based upon the mass, right? So on the right you see massive stars, and the definition of a massive star is the mass is like 8 to 10 times the mass of the sun, and anything below that we call it a lower intermediate mass star. The sun is also a lower intermediate mass star. So we clearly see a difference between the phases of evolution between both types of stars. And you can't see it in this picture, but the massive stars do not have an AGB phase. So we are solely going to talk about the lower intermediate mass stars. Right? I also want you to note the end of both kinds of stars. So the massive stars end their life in a supernova, and whatever remains will either be a black hole or neutron star. So we know this, but on the other hand, the lower intermediate mass stars, they end their life by becoming a white ball. Okay. So now that we have established that, I'll introduce you to something known as Hertzsprung-Russell diagram, or more commonly known as the HR diagram. So on the y-axis, you see the luminosity. Luminosity is just the rate of energy that is being emitted by a star, and on the x-axis you see the temperature, right? So all the labels that you see are different phases of stellar evolution. So every star starts its fusion by fusing hydrogen into helium, and when it does, the luminosity and temperature lie on the main sequence. So basically every star starts out as a main sequence star. Right. But then, since it is burning hydrogen, it will eventually run out of hydrogen in the core. And once it does run out of hydrogen, there is no radiation pressure to balance out the gravitational pressure. So what happens? The star starts to contract, and as it contracts, it leaves the main sequence. And when it contracts, the temperature gets high enough for hydrogen fusion to start again, but not in the core, because there is no hydrogen in the core anymore. But around the core, the hydrogen burns in a shell surrounding the core, and that provides the radiation pressure to balance out the gravitational pressure, right? the star keeps contracting, the core keeps contracting because there is no radiation pressure from the core. But when the shell fusion starts, the energy output is much more than what it used to be in the core. And the sudden increase in energy causes the outer envelopes of the star to expand. This is when the star gets very huge. So you see in this picture, that is the red giant. Red giant is when the star gets really big. So our sun, when it becomes a red giant, it gets so big that almost close to Jupiter. Right. Okay, back to the HR diagram. So we now have hydrogen fusion in the shell. The core is contracting, the outer layers are expanding, and eventually the core contracts enough, and the temperatures rise high enough for helium fusion to be possible. So that's when helium fusion starts, and that's when the red giant branch phase ends. So now all the stars after the red giant branch phase, they lie on the horizontal branch. Horizontal branch because it's almost horizontal. Okay, and before that, red giant branch because giant because it gets huge, and red because it gets cooler. Because the outer layers expand. Okay. And so in the horizontal branch, what do we have? We have helium fusion in the core and hydrogen fusion in the shell. Right? And eventually, the same thing happens. The core is going to run out of fuel. So helium is going to get exhausted too. And the same thing happens again. Which is when the star leaves the horizontal branch and starts climbing up the asymptotic giant branch. Asymptotic giant branch, when you shorten it, becomes AGB. So this is the phase where if the star is in this phase, it is called an AGB star. Right? And so in the AGB phase, there is no fusion in the core anymore, because all the helium also has been exhausted, and the mass is not high enough for further fusion to happen. But what happens is, previously we had a hydrogen shell fusion, and adding to that we'll have helium shell fusion. So now we have two shells providing energy and a core that's not fusing anymore. This is when the star climbs up the asymptotic giant branch, and after that's done, we have the post-asymptotic giant branch. This is basically the post-AGB star. At the end of the post-AGB star, we have a planetary nebula, possibly. Yeah. So now we're going. So basically, all the early phases we don't care about when it comes to post-AGB star, because all the observables that we are interested in for a post-AGB star are because of the processes that happen in the asymptotic giant branch phase. Right? So we'll now go into detail about the AGB phase. So what do we have? We have two shells that facilitate fusion, but for different elements. And as the helium shell burns, it gets thinner, and the shell gets so thin that it gets prone to instabilities. So basically, when you work out the math, what you get is any small perturbation in temperature will naturally cause the shell to expand, and that means, and when you work out the math, you see that any change in the size of the shell will cause a temperature rise. So this kind of becomes a feedback loop where the temperature rise leads to the shell getting bigger, and the shell getting bigger leads to temperature rise. So eventually, what you have is a lot of energy, which is basically a flash. And in this flash, a lot of energy is produced, and all the helium in the shell is exhausted, most of it. And due to the sudden release of energy, the outer layers expand again. And when they expand, the temperature again gets cool, and the hydrogen shell fusion is extinguished, most of it. So now we only have some of the hydrogen, the energy produced in the hydrogen fusion to support the star. So basically, this process continues in an AGB phase. So first you have the thermal pulse, and then you have and when the star expands enough, it cools down and it starts to contract again. And as it contracts, there is a very important process that happens, which is called dredge up. This is basically the nucleosynthesis products that formed in the star are dredged back up to the surface, near the surface, right? And then after that, the star cools down and the hydrogen fusion in the shell produces helium. And when the helium builds up enough, we will have another helium flash. So when the star cools down, it becomes convected. So all the things get mixed up. And so one more thing to notice: when the star expands, as I mentioned, it gets really huge. So the outer layers are very loosely held onto the star. So they can be very easily lost due to radiation pressure. We call it, the star uses it in what we call a stellar wind. And also, there is a very important nucleosynthesis process that happens during the AGB phase, which we are going to detail later. But it is called the slow neutron capture. Right? So now that we have talked about the AGB phase, we are now in a position to talk about post-AGB phase. So as I previously mentioned, the observables expected are the pre-post AGB phase, which is just the AGB phase. So when does a star actually end its AGB phase and start its post-AGB phase? The common consensus is when a star loses almost all of its mass except 10 to the power minus 7 solar masses, that is when we consider the star to be in the post-AGB phase. And as it loses mass, we establish that it loses mass, right, in pulses. So as it loses mass, the star gets hotter and hotter because like the inner layers of stars are hotter. So as you lose mass, what you have is hotter star. And as we previously mentioned, the end product possibly is a planetary nebula, and what is left of the star is a white dwarf. Now that we have talked about post-AGB phase also, we can talk about the post-AGB star. Naturally, the star in its post-AGB phase is called post-AGB star. Right? And the post-AGB star has two components. So the mass that it loses and it itself. The mass that it loses surrounds the central star, which is called the circumstellar environment. The circumstellar environment is made up of dust and gas. And then there is the central star. So we are going to talk about both of these components and what we can observe from both of these components. And since the central star is covered in the circumstellar environment, it is not every time that we can observe the central star. Which is why in the image that I showed earlier, you didn't see most of the stars. That's what that was. Before we go any further, let's ask a normal question. Why do we care about post-AGB stars? And to illustrate one of the reasons, these are 4 images of planetary nebulae. The images are taken by and the images are invisible and UV. Yeah, that's it. But what is important and what I want you to notice is the structure of planetary nebulae. Sure, the color is compelling, but also the structure is very complex, right? And so the colors that you see are not made up. So sure, the X-ray colors are made up, but there are also a lot of visual colors, and that is because the gas is ionized by the central star. So when it ionizes the gas, they emit light. And yeah, throughout this talk I've been mentioning that possibly a planetary nebula, possibly a planetary nebula, and that is because planetary nebula is not always guaranteed, right? So when the star loses its mass, the mass isn't just going to move a certain bit and stay there. The mass keeps expanding. So the circumstellar environment keeps expanding. And for the central star to ionize the gas, it needs to be hot enough. And to get hot enough, it needs to get smaller enough, right? But if once it gets hot enough, if there isn't gas surrounding it, the radiating photons will just go away. So they don't ionize the gas. So you don't necessarily have a planetary nebula for every star. So you see all the complex structure that is so visually compelling. But now we will go back a few thousand years in time. This is what you have when you go back a few thousand years. This is an AGV star that was captured by our telescope. And you see the temperature 3000 Kelvin and the luminosity that is 10 to the power 3. So in the Hertzsprung-Russell diagram that I have shown earlier, this star falls near the end of the AGV phase. Right? So it is at the end of its AGV phase, which means it is going to go into post AGV phase. So what really happened between the end of the AGV phase and planetary nebula? As you can see, all the complex structures that you see in the planetary nebula is not there in the AGV star. It's just a spherically symmetric mass loss. But when you get to the planetary nebula, everything's changed. So what exactly happened? Whatever happened in the posterior phase, right? So, and findings have shown that it's not even in the early posterior phase that this transition from being spherically symmetric to the complex structure that we observe. So to understand how this happens, or rather what happens, we need to study posterior stars. To understand what the mass loss mechanism is, what the mass loss mechanisms are, we need to study posterior stars. And by studying them, we need high resolution images of the circumstellar environment. So we need the high resolution images, and for high resolution images, we need to image posterior stars. And to image posterior stars, we need posterior stars, right? And to have posterior stars, we need to identify posterior stars. But the problem is that posterior stars are very rare and hard to find. And the 5 of you that read the abstract know this. But we have in our galaxy around 500 candidate posterior stars. And that's out of the hundreds of millions of stars there are. And part of the reason is that the posterior phase only lasts for around 1,000 to 10,000 years. So when I said going back a few thousand years, that kind of gave away. So despite all of this, how do you find these stars? We actually found 500 stars, right? How do you find more? The 500 candidate posterior stars that we found are found using infrared data, because as we've established, you can only see them in infrared, mostly in infrared. So the data is from the Infrared Astronomical Satellite (IRAS), and the data were published in 1980s. So from 1980s to this day, we have been working with the IRAS data and the 500 posterior candidates. So how do we find more? To find more, we need new IR data. Right? The Wide Field Infrared Explorer is a sky survey and has over 7 billion stars and infrared data. And the data were released in 2013. So it offers us many hidden posterior stars. Hence, now the question is, how do you actually find them? Well, to find posterior stars, I'll introduce you to something new again. photospheric models. What you do is you model the atmospheric, your stellar atmosphere. And once you do that, you get an estimate of the fluxes the star emits across the wavelength range. And these models are typically made on three parameters: the effective temperature, the surface gravity, and metallicity. And once you have a model, you feed it to observational data. Why is that helpful? We'll get to it in two slides. First, we'll come back to dust again. So as we talk about dust, comes in a whole range of sizes, and the composition can range from silicate grains to PHs, right? And important, or rather, the only property that we care about is that it absorbs wavelength, shorter wavelengths, and it emits in infrared. And yeah, AGV stars lose mass, and the lost mass forms dust, and so post AGV star is covered in dust. So if you piece everything together, you have this. So the grey line that you can barely see is the flux that you get from the photospheric model. And the dotted red line is the dust emission field. Combined, you get blue spectrum. Right? So the fact that you have more flux in the infrared than what you expected from the photospheric models, that is called infrared excess. We have an excess in the infrared. So surely whatever has dust around it, the dust will emit in infrared, and so you will have infrared excess. So since post-AGV stars are covered in dust, you expect infrared excess from post-AGV stars. But the question, the IR excess doesn't guarantee you a post-AGV star, because other stars can also have dust around. If you go back to the first image that we showed, when we showed the stellar life cycle, we saw that the stars were forming out of a star forming nebula. Right? And so when a star just forms, it is covered in dust. So the young stars are also covered in dust. So you expect infrared excess from both young stars and post-AGV stars. So just from the infrared excess, you can't say that it's a post-AGV star. But more importantly, the question is, how do you differentiate between young stars and post-AGV stars? To be able to do that, we talk about color. So just from looking at these circles, you can say what color each of these are. Although I've written them, but you can tell what color these are, right? This is the common notion of color. So let's say you have joined the astrophotography subcommittee, and you have seen this picture. This is the Lagoon Nebula, and if you were tasked with finding blue stars and red stars from this image, although I don't know if you can see from there, but red star. What? Yeah, so if you observe carefully, you will be able to differentiate some red stars from all the blue stars. So basically the point is, if you want to know what color a star is, at least from this image, you can tell just by looking. But what if you have this? What you have is the idea of a star and its fluxes in different filters. So a filter allows light of certain wavelength range. Right? So let's say for the first filter, B, it allows blue light. So if you were tasked with ordering these stars based on how blue they are, the natural instinct is just to take the fluxes in the blue filter, and whatever has higher flux in the blue filter is a bluer star. Right? That is the first star you get, and it is not so wrong. But there is a problem with that. The problem with that is that the star can just be bright. So although you may see what?
What
just be bright. Star can just be bright, so it can have a higher flux compared to all the stars, but it can have a lower flux in the red field, which you are not considering. So to address this problem, the solution is B minus B. What is B minus B? So you see the filter on the right, that is B, which is basically allows green and yellow light. So when you subtract the fluxes in both these filters, you take out that factor of brightness. So for example, consider a yellow star, but it is very bright, that it has fluxes that are close to an actual blue star. So just from the blue filter, you wouldn't be able to tell what is a yellow star and what is a blue star. But when you subtract B minus V, you do B minus V, since the star is a yellow star, the B minus V becomes negative. But when you take an actual blue star, the yellow light is going to be less than the blue light. So what you will have is a positive color. So once you take the difference, you can actually tell what color a star is. So, but you can only learn so much from just one color about a star. Which is why we will take two colors. So this is what we call a color-colored diagram, because there is a color, there is a color. And on the axis we have so the IR 12, 25 and 60 that you see, those are the names of infrared bands of the IRIS machine that we showed earlier. So the color-colored diagrams have been very helpful in finding those 500 post-AGB candidates. What you basically do is, so the AGB stars that are in red and blue, they lie somewhere on the left. They are clustered towards the left side. And the planetary nebulae that are the red triangles, those are on the right side. So what you do is you take stars between these AGB stars and planetary nebulae, and you will possibly have a post-AGB star, which are the green dots. IR 12 is a band, IR 25 is a band. So, what height? 25. So, now that you have color diagrams, and we also have IRS. We have two things that can help us identify post-AGB stars. We'll get to the third one, which is, okay, before we get to the third one, there is another class of other kind of images that are also just as helpful as a color diagram. But to introduce that diagram, we need to talk about what absolute magnitude is. And the absolute magnitude is how bright the star actually is. And what we observe is the apparent magnitude. So, to define magnitude, the magnitude is defined as minus 2.5 log of flux. And so, if you take the difference between the absolute magnitude, which is capital N, and the apparent magnitude, which is small n, what you basically get is the ratio of the fluxes and the log of them. And we have the fluxes inversely proportional to the square of distance between us and the star. And the standard notation is the absolute magnitude is minus 2.5 log the flux at 10 parsecs away from the star. So you basically have the relation shown in the second equation. And when you use the first two equations, you get the third equation. This basically gives you, so you have the apparent magnitude and you have the distance between you and the star. So you can get the absolute magnitude, how bright the star actually is. Now that we have talked about absolute magnitude, we are ready to get to the other diagram, which is the color magnitude diagram. As the name suggests, you just replace one of the color and color diagrams with a magnitude. Okay? And you have actually